Welcome to today's webinar, which is hosted by Maya HTT. My name's Adrian Perico. I'm a Senior Pre-Sales Specialist here at Maya, and I will be your presenter. Our webinar is titled Comprehensive Electric Motor Prototyping. Our discussion today will focus on electric motors and electric vehicle systems. Specifically, how virtual prototyping can produce an optimal electric motor operating within an optimal electrical vehicle system, complete with how the cooling system is developed for keeping the electric motor within an acceptable temperature range. Our webinar will be split into two parts. Part 1, reviewing the electromagnetic performance of an electric motor using a software developed by Siemens Digital Industry Software, or simply Siemens DISW. Software is called Simcenter e-machine design. Part 2 will be reviewing the thermal performance of an electric motor within a system using another software developed by Siemens DISW. The software is called Simcenter e-machine. First, we'll explore the process of evaluating electric motor design alternatives with Simcenter e-machine design. Simcenter e-machine design is an app which enables the virtual prototyping of electric motors or generators. It runs on any current Windows-based PC, and it sports a modern template-driven interface. Simcenter e-machine design allows you to replicate a physical motor by constructing a virtual equivalent. And then you can quickly execute a range of standard experiments on the motor to collect your desired performance metrics. The Simcenter e-machine design workflow has the following 7 steps, which we will explore independently. You'll find that in each step of the process, the required details are a combination of configuration pull-downs with multiple options to choose from, and a series of text fields where numerical values must be entered. The first step in the workflow is the General Settings interface. Here we can see the basic parameters which describe your electric motor candidate. And more clearly, here's a magnified view. Once the general settings have been configured, we can move on to step 2 and consider the pertinent details for defining the specific topology of the rotor. The details are shown in the rectangles, and here with a zoom in for better visibility. After the rotor topology has been configured, we can move on to step 3 and review the details for defining the topology of the stator. The details can be seen in the orange outlines, and the magnified view lets us review them much more easily. Our fourth step will be to configure the phase winding. The possibilities are shown here. And we can see them more easily with this zoomed-in view. Note the Simcenter e-machine design boasts the only automatic layout calculator in the industry. All possible balanced windings for a specific rotor pole stator slot combination are calculated. These alternatives are provided enough pull-down and can be selected by the user. Copies of the base design can be created, and then each copy can reflect one of the alternate layouts. Experiments will then reveal to us how the various alternatives impact the motor's performance. We have now finished the physical details and can move on to the 5th step in the workflow, assigning the materials for each component. Simcenter e-machine design boasts more than 20 libraries of possible materials, with more than 400 total materials to choose from. All materials are defined as a function of temperature. Where applicable, nonlinear tables are also used to accurately reflect the electromagnetic behavior. Simply use the pull-downs to scroll, locate, and assign each component to your desired material. Stacking factors are also available with other relevant parameters so that you can best represent the component's expected behavior. With our motor fully described, we can move on to step 6 and execute experiments for the motor, just as we would in the laboratory with a physical candidate. Simcenter e-machine design offers numerous experiments to choose from. The appropriate input conditions for each experiment are automatically set up for you, and you don't have to worry about the details. You simply execute the experiment, review the results, and collect all of your desired performance data. In the interest of time today, we'll cover just a few of the possible experiments within our virtual laboratory. Here we have a chart depicting the result of the cogging torque experiment. Notice that you can review the curve with a rubber band mode, which allows you to trace the full line and see the XY coordinate values at each data point. Additionally, you can review a table with all the XY values, or you can export the data to Microsoft Excel. Finally, the data from each experiment can be easily logged into Simcenter eMachine Design's laboratory notebook, referred to as the report. The report is resident in the model file and can be accessed any time for candidate comparisons or for sharing during a design review. This chart depicts the result from the torque versus speed experiment. The results show the time average torque data at several speeds throughout the range that you defined. This color shade plot depicts the result from the efficiency map experiment. Simcenter eMachine Design comes with the ability for you to execute a time-transient finite element method, or FEM experiment. This is the highest fidelity experiment, which reveals things like saturation, induced eddy currents, and other second-order effects. You have several options for reviewing the result, including a table like this one, where the time average data for performance indicators are listed. Or you can see the waveform response for a specific global quantity, like the torque shown here as a function of time. And finally, you can elect to have an FFT applied to a quantity of interest so that you can review the harmonic content. Because Simcenter eMachine Design utilizes FEM as the foundation for all of its experiments, it is possible to review microscopic details of the electric motor. And this extends your review of the motor beyond what is possible in a typical laboratory. Take, for instance, this graphic showcasing a shade plot of the magnetic flux density. B fields are shown throughout the cross-section of each component in the electric motor. This zoom-in details or highlights that you can also use a point probe to more precisely review the flux densities. Any desired location can be defined, and the resulting flux density is easily collected to be compared against other design candidates. Another really cool result of the FEM experiment is that you can review how losses are induced into each component. The first video showcasing the time average hysteresis losses induced throughout the cross-section of the laminations. Second video shows the induced eddy current losses in each component, including those within each of the permanent magnets. Our seventh final step, after we have determined a suitable motor candidate, is to transfer all of the pertinent details from Simcenter eMachine Design to Simcenter AIMSIM using this simple export. Before we move on to the thermal part of this webinar, we are going to take a quick look at the fully described system which makes up the electric vehicle that our motor fits into. Here we can see the detail of a comprehensive electric vehicle system. There are many components in the system, and each one is appropriately connected to its neighbor as its role in the system would dictate. Additionally, each component has special characteristics which reflect its transfer function. In other words, how it performs relative to any changes to its inputs. We're not going to review all the details for each component, but we will show the comprehensive nature of the system by highlighting a few of the key components. Our first detailed look into the system is the combination of the vehicle, the road, and the environment components. There are a variety of parameters for each one of these pieces. As a partial list, we can control the following sorts of things: vehicle aerodynamics, wheel and tire sizes, the road layout, whether it's flat, hilly, straight, or twisty, the road surface, whether it's dry or wet or perhaps icy, the outside temperature, and whether or not there's any wind that's impacting the movement of the vehicle. Our next components to review are the electric motor and drivetrain. Parameters here allow us to control these sorts of things: the torque delivered to the shaft, losses generated by the electric motor, gear ratio, which controls the torque delivered to the wheels, and the efficiency of any transfer of energy. Our final component to highlight in the electric vehicle system is the cooling system of the electric motor. This component will determine whether we can remove the heat and keep the motor operating within an acceptable temperature range. This is a very specialized component called a supercomponent. It is a comprehensive lumped parameter thermal network, or LPTN, and it's used for portraying the thermal behavior within the motor. With our electric vehicle system in place, we will now initiate the special Simcenter AIMSIM app called the eMachine Thermal Network Tool. This app collects all the motor details within Simcenter eMachine Design and then uses them to construct the LPTN. The LPTN includes all the geometry information for both the rotor and the stator. It also includes material definitions. The LPTN includes the values for all EMAG losses. And these losses are used as inputs to the thermal simulation and will directly impact how the motor heats up. The LPTN accounts for the heat dispersion in both the radial and axial directions in the motor. The LPTN includes elements for describing the conduction, natural convection, and radiation thermal physics. As the app constructs the LPTN, it also allows us to add cooling strategies. You can pick from among the available forced convection fluid cooling strategies and try to remove the heat. With the review of our electric vehicle system complete, we can now turn our full attention to the LPTN, and we will have a look at whether we can successfully cool the motor. Let's have a closer look at the capability constructed by the app in the LPTN. There are 5 pieces which make up the foundational thermal technology, and all of these are represented by their own supercomponent. First, we have the end plates, one for each side of the motor. Second, we have the housing. Third, we have the stator. Fourth, we have the air gap. And finally, we have the 5th supercomponent, the one for the rotor. Each of these items in the LPTN is a physics-based network behind the scenes which describes the dispersion of the thermal energy. To assess the thermal response of any electric motor, we need to energize it with specific requirements of operation over a defined period of time. We'll call this the drive cycle. Here's the drive cycle which was used for our consideration today. The full drive cycle is 1200 seconds, or a 20-minute duration. The vehicle starts from a resting or stop position, and it accelerates for 400 seconds until a speed of 144 kilometers per hour is reached. The vehicle then continues at this cruising speed for an additional 800 seconds. At this point, we'll use the LPTN to explore what temperatures will result when we review 4 different cooling strategies. These are all shown below. Our first experiment with the LPTN will explore how the components in the electric motor respond when no forced convection fluid cooling is present. We see here 2 charts where the temperature response of each component of the motor is portrayed versus time. I've split out the components into 2 groups so that the individual component lines are easier to look at. A quick review of the component temperature shows us that all of them exceed 100 degrees C, and some components reach nearly 130 degrees C. Our conclusion here is that the electric motor will not operate at suitable temperatures and would be in danger of overheating during our drive cycle. Now we will add the first form of forced convection cooling to the motor and see what happens. Specifically, we have added the TEFC cooling during our use of the app. This is outlined in the orange rectangle. The TEFC configuration implies that a fluid, air in our case, is being passed over the outer surface of the housing. The housing will have a series of fins and perhaps a shroud or cover to focus the flow of the fluid for a more even pressure drop and better cooling. In our example, we've configured the housing to include 68 fins with an axial orientation, and the fins are spaced approximately 20 millimeters apart as they are placed around the perimeter of the housing. Each fin is 2 millimeters thick and has a 15 millimeter height. How much cooling takes place as we review 2 different flow rates for the air that is passing over the fins. Our first set of graphs here are for a flow rate of 1 liter per minute. Here are the resulting temperatures. Notice that there's a minor impact on the temperatures in the form of a reduction. Our second flow rate is 10 liters per minute. And although the temperatures for each component are reduced more than the first flow rate, and they're all below 100 degrees C, they have still not reached an acceptable temperature. And further, they're not trending towards stabilized temperatures, and the vehicle's motor would be in danger of overheating during the drive cycle or with any extensions beyond the drive cycle. Here we will explore the second form of forced convection cooling, specifically duct cooling. In this scenario, the ducts are constructed as part of the housing water jacket. In the water jacket, fluid passes through a series of ducts or channels which are manufactured within the thickness of the housing wall. Typically, the ducts would be either in a spiral or serpentine pattern. Our water jacket includes 3 spiraling turns along the stator stack length. The duct has a 3 millimeter by 11 millimeter cross section, and we're going to pass a fluid of ethylene glycol and water mix with a 50 percentage. How did things cool down? We'll have a look at as we explore 2 different flow rates for the fluid passing through the channels in the housing. With the first flow rate of 1 liter per minute, here are the resulting temperatures. There's a reduction of the temperatures, but the temperatures have not stabilized and are still trending upwards. With the second flow rate of 5 milliliters per minute, we can see that the temperatures for each component have been reduced to acceptable temperatures. And furthermore, the temperatures are all stabilized, and we can imagine that the driver could extend operation beyond the 20 minutes of our drive cycle without damaging the motor. Our final cooling configuration in the LPTN will now be considered. Here we've chosen to add spray cooling with our use of the app. This is outlined in the orange rectangle. This form of cooling consists of an array of fixed nozzles mounted in the end region on both sides of the motor. These nozzles project a constant spray of fluid onto both the end windings of the stator and the end surfaces of the rotor. We've configured the spray cooling to include 8 nozzles for each of the stator ends and 8 nozzles for each of the rotor ends. All 32 nozzles have a 1 millimeter diameter opening, and we're going to project a cooling fluid, which is a mixture of ethylene glycol and water with a 50-50 mixture. Once again, we've experimented with 2 different flow rates for the fluid. The first flow rate is a half a liter per minute. Here are the resulting temperatures. There is some reduction of the temperatures, but the temperatures have not stabilized and are still too hot for safe operation. Our second flow rate is 3 liters per minute. Here the temperatures for each component have been reduced significantly down to a very nice range. All are less than 60 degrees C, and they have stabilized so that the driver could easily extend operation beyond the 20-minute drive cycle without fear of damaging the motor. Our discussion today is focused on the virtual prototyping of electric motors. Our webinar was split into 2 parts. We reviewed the electromagnetic performance of an electric motor within a software called Simcenter eMachine Design. Using this app, we were able to review how we might produce a suitable electric motor candidate. Part 2, we reviewed the thermal performance of the electric motor within a software called Simcenter AIMSIM using a revolutionary LPTN technology. We showed that our electric motor candidate will heat up during our defined drive cycle and that this heat would very quickly degrade performance and possibly cause the motor to fail. Knowing that the motor needed to be cooled down, we then determined 2 potential cooling strategies which successfully took away the heat and allowed the motor to operate at acceptable temperatures during the drive cycle. We trust that you've seen the power of the capabilities from both software. We want to thank you for your time and attention today. As we close our webinar, we would like to acknowledge the contribution by our colleagues at Siemens DISW. A big thank you to Landry Sozal, Florent Pasteur, and Cola Flamand. Thanks for watching. Please feel free to reach out to me if you have any questions.